talk about Apache Spark and MLlib. If I can use my remote correctly. Okay, in this talk we're going to be in two parts. One is like, what is Apache Spark? How do I use it? What is the function of the whole thing in general? Second would be the MLlib library and what kind of tools I can use that for, what kind of projects. So first, what is Apache Spark? Let's get started by talking about data. We're drowning in it. It's everywhere. It's not necessarily a new thing. It's just we've just now realized that there is data in literally everything that we do. Our watches are counting steps as we walk. Every time we tweet or we do a Facebook like that's kind of common, but there's so much data generated from everything. I'm pretty sure I've seen apps where you can track your bowel movements and do all kinds of stuff. There's just data in every possible area that you can imagine. It's everywhere. It's everything that we do, and it's unlimited. It never ends. Data is just a numerical representation of our existence. Like, you can track it, everything from your Facebook lights to spinning electrons and spinning galaxies. It's just literally everything. And it feels like it's a new thing, but really, it's always been there. We're just now kind of opening our eyes to it. Every action in your business, every user that goes to your application, every time you walk to the store to get a coffee, you're generating some amount of either continuous or discrete data that has to get stored somewhere and then analyzed. So it's big. And you can probably imagine what term this goes into, but it truly is big. The actual size of data is immeasurable. We have a pretty good idea of how much data we store, but we have no idea how much data is in existence that we haven't even encountered yet. So, big data is hard. And there's really, this thing likes to change if I point it right at it, so I need to remember that. Big data is hard, and there's really three main challenges. First is capturing. How do we get all that data? There's fitness companies, probably 10 years or so ago, figuring out how we can collect data for people who like to run and ride bikes. How can we collect that data and then give a user a cool representation of the actions that they are taking? Then came in fitness watches and sensors you can put on your bicycle. How do we collect our data that our users are using in our applications? We have a lot of profiling and metrics data that come from our applications with every single click and everything that you type in. So that's the first problem. How do we even capture it all? It's everywhere. So now we've got it. So let's assume we've figured out how to capture all of the data. How do we store it? You can't put it all on one hard drive. It's so much data. You've probably heard where Facebook and Twitter, they have petabytes and petabytes of data. How do we store it is then the next big problem, because it grows at an exponential rate every single day. And then the third would be analyzing. We've collected all the data. We've figured out a way to store it. How do we then quickly pull that data to do analysis on it and run queries on it? Because if we've stored it all, it's doing nothing as it's sitting there. And that's really where a lot of businesses kind of stop with big data. They think big data is just collecting it and storing it, and then they can go to a conference or a trade show and say, we are a big data company. And just because you have a shit ton of books in your library doesn't mean you're like a really awesomely read person. You have to actually use the data. So the third one is analyzing. And this problem is compounding on each other as we go through each step. We've now figured out how to store massive amounts of data that we can't even imagine. Now, how do we analyze it? So for a real-world example, we'll do with tweets. Tacos are the best. Tom Brady is the best, so Tom Brady is tacos. So this is your average tweet. I didn't say this, but I do agree with this statement. So a tweet is around 200 bytes. Really small, tiny. Your tweet is nothing. Yeah, I'll put that on my hard drive. We'll run Twitter on a MacBook Pro. But Twitter is generating around 6,000 tweets per second. At 6,000 tweets per second, that comes out to around 350,000 tweets per minute and 500 million tweets per day. So 200 bytes is starting to sound like a real problem. 200 bytes, 6,000 tweets a second, come out to 12 megabytes a second, times 24 hours, you're looking at 1 terabyte of data just for Twitter. And when I say just for Twitter, this is really just a tweet as well. It's not the metadata that you may derive from Twitter. If you want to, with each tweet, you pull out the replies, the hashtags, their geolocation. Now you're probably dealing with the order of 600, 700 bytes per tweet, given all the metadata that you need to collect and derive. Excuse me, and of course this comes out to around 30 terabytes a month. It's a lot of data, it's not crazy, but this compounds every single month, and unless you're running your business for a single month, you've got a serious problem in like 6 months to a year. How do we deal with this? And that's really just Twitter on an average day. That's not talking about the Super Bowl, where this is going to actually probably multiply out, I forget the exact number, but on the order of hundreds. For events such as this. The election debates lately have been generating massive amounts of tweets. So big data is not bullshit at all. It's been co-opted as a business term that's kind of been removed from what we believe it to be as developers, and we kind of see it as a bullshit word. But as developers, it is a serious problem, and we're dealing with solving that every single day. So back to these 3 challenges. Spark is going to help us solve analyzing. So capturing and storing is a totally different problem, a different talk. With capturing, you've got streaming services like Ganip for Twitter. With storing, of course, we have the big gorilla of HDFS and Hadoop. But for analyzing, we've had MapReduce, but it's been relatively slow. Spark was developed at MLlib at UC Berkeley as a new way to do this analysis process. MapReduce works on a batch job type basis. We need to find a way to calculate data as it's streaming through and do it in a faster way. One thing to note with Spark is not a better Hadoop. Hadoop is a totally different thing. Hadoop solves our storage problem. We have HDFS, which is the Hadoop file system. That allows us to, we no longer have to worry about putting data on one machine. We can now distribute data across thousands of machines. Yahoo's Hadoop cluster, for example, is over 8,000 nodes, petabytes and hundreds of petabytes of data. This damn remote, and it's not a better Hadoop. However, you could say that Spark is a better MapReduce. You can do MapReduce problems on Spark, but it's kind of a different paradigm, which I'll talk about. The big thing that Spark brought to the table as an innovation was that it works in memory and not on disk. With every MapReduce job, you're incurring 3 times the data size that you are working with in replication and disk writes, with disk I/O and network I/O. So every time you do a job, it's a batch job, pulls all the data from disk, runs your calculations, then writes your data back to HDFS. The next job kicks up, it pulls that data from disk, goes through the same cycle. If you're dealing with a single job MapReduce, maybe it's not too big of a deal, but if you've chained together hundreds or dozens of analytics kind of checkpoints, this is an extreme amount of disk I/O at every step of the game. Spark brought everything to an in-memory system. We're now dealing with RAM as opposed to the disk. And this was a big innovation that we couldn't really deal with in 2011 when Hadoop came out, because there weren't massive, cheap RAM disks with, I think on the largest one you can get on AWS is probably like 128 gigabytes or something of RAM on like a single machine. It's crazy amount of the amount of RAM that you can get on a cheap level. So Spark came in and said, why don't we distribute that data across RAM as opposed to disk? It also uses a new paradigm called the resilient distributed data set. And if you've ever done any data science, you've probably heard of the acronym RDD, which is what this stands for. So this data structure is a format that allows you to structure data across the cluster in RAM. So how this actually works is an RDD has a list of partitions where it breaks your data up automatically into sections, and then it maps those partitions in the RDD to then RAM partitions across your nodes. It does this automatically when you initiate the RDD on the system. So kind of a visualization of how the RDD actually works. You have some sort of data array, and really it could just be an array. It could be an array of tuples or some other data set, but you initialize it as an RDD, and that parallelizes it across the entire cluster. It then automatically breaks it into partitions, and it does this automatically in a smart way. You can define your own partition functions, but basically at the lowest level, you can just throw it into an RDD. It automatically creates the partitions and then maps those to available hosts in your cluster. So certain chunks of your data will go to different hosts, but you still interact with it as if it was a single host. And that's the innovation that Spark brought to the table, this in-RAM distributed data store where you interact as a single point of entry across an entire cluster. So we now have this system that allows us to do much faster calculations. And a stat that I forgot to mention was Spark, due to working in RAM as opposed to on disk, is working at 100x speed of MapReduce on Hadoop, due to the fact that they're working in RAM as opposed to disk. However, you should note that Spark can do on-disk operations, and even with on-disk operations, Spark is still 10x faster than Hadoop. So it's something to look into if you have a Hadoop cluster that you're running MapReduce jobs on. You could get a very quick and easy 10x speed increase while still doing on-disk operations, batch operations. But with Spark, we don't want to really deal with on-disk operations because the real bread and butter of Spark is in memory. So we have this really fast system to do calculations. We have this really big problem where we need to do massive calculations on large data sets in order to predict and analyze data that we're collecting. So why don't we do machine learning on Spark? Machine learning has a lot of options in the community. There's scikit-learn, which is a really big one in Python. There's a lot of libraries in R and MATLAB. If you've been in academia, there's a lot of stuff that you have available. But Spark specifically has a built-in library called MLlib. And in MLlib, we've built, not me, we have available a lot of algorithms that we can use for all of the various sections of machine learning that we may use in our jobs. So why would you use MLlib as opposed to scikit-learn? PySpark is a Python interface to Spark. You have Python, you have access to scikit-learn. You could do calculations with scikit-learn using Python just in general. But MLlib is built at the core to interoperate with Spark. It's built on Spark, for Spark, by the Spark people. So getting that 100x increase that we have with the advent of RAM-based calculations and storage, the ML algorithms that we use become much cheaper to run on a quick basis, as opposed to running a MapReduce batch job overnight where you're going to calculate new data that your system will have available for you tomorrow. You can now do streaming updates as tweets are coming into your system. So we've learned a little bit about Spark. Big things are in memory, 100x faster. How do we use MLlib? As I said, MLlib is a machine learning toolbox that's really integrated with Spark. The key thing that makes it awesome is that it has this RDD API. That allows you to distribute these standard machine learning algorithms that we use all the time across a cluster of machines. And it does that without our interaction. It will deploy a certain subset of operations to one host to work on a smaller set of the data, and then pull that back into a single result set at the end. In MLlib, we have your standard categories for machine learning, and these algorithms are built in. There's actually much more than these. For classification, you have your standard regression and naive Bayes type stuff. You'd use this for sentiment analysis, classifying documents for themes, for genres. For example, if you had a list of text documents, you want to figure out what kind of themes people were talking about. Topic modeling also goes into figuring out topics. You have the LDA algorithm. You have your standard regressions that you may have learned in your math classes, your stats classes. decision trees, clustering. One specifically we're going to talk about in this talk is building a recommendation engine for products. This is, when I say products, it just goes to recommending something to some group of users. So specifically, an example you're probably familiar with is Netflix's movie recommendation engine. It's built on the same algorithm, much more advanced, obviously, than the one I'm going to show you. But it's the same basic math. And building the recommendation engine, we're going to use MLlib's alternating least squares algorithm. So the technique that this recommendation engine is built on is called collaborative filtering. So we do this all the time in Amazon, in Netflix, when you're rating products. It's the 1 to 5 stars thing. When you're looking at Amazon, you see a product, you buy it, you think that it's okay, so you give it a 2. This one's really awesome, it gives a 5. But that data is compounding every time a user is rating. You're collaborating with other users in order to filter down to an appropriate product. So it's pretty basic. You have a user who's saying either, yes, I like this, or no, I did not like this. However, you start to build a network of how all of those things are built together. In this example, we only have 4 users. But we know this person didn't enjoy this book. This lady did not like this beer. Everyone likes PlayStation. And you can see that these products don't even need to be the same products. We're not doing analysis based on the attributes of how are horror movies relating to comedy movies. This can be a genericized thing where we're just dealing with an object. And in this case, the object is PlayStation, beer, Blu-ray disc, and a book. So this is happening every day on Amazon. People are voting up or down. You have more people who are voting, and the network starts to grow. So now we see this graph of how all of these product ratings are going every single day from individual people that they may not necessarily be friends. You know, Amazon, you're just dealing with all the consumers in the entire corpus. But it could be an algorithm that you could run with your Facebook friends. Among my friends, what would you recommend that I would like? But you may see that we've got 3 HD DVD holdouts here on the Blu-ray. They're really sticking to that HD DVD, but we don't know if this girl likes the PlayStation. That's a missing link in our graph. So how do we figure, and using this data, how do we figure out the best way we can to recommend if she's going to like the PlayStation or not? So we take that graph, which is a little bit to absorb. We've only got 4 users here as well. Imagine we're dealing with 200 million consumers shopping on like Amazon every single day. So let's break it into something a little more readable. It's just a table. It's the exact same data, but we have some gaps here. How does she feel about this book? How does she feel about PlayStation? How can we use this data to recommend if they're going to like or dislike this product? And that's really the main problem that collaborative filtering is trying to solve. Using the kind of the binary look at it, it's either good or bad, is interesting. But to really get into these calculations, we're doing statistics. We could say this is 0 or 1, but it'd be much better to give a really good approximation if we're dealing with like a 1 to 5. And this is what you see on Netflix or Amazon. It's a 1 to 5 star thing. I'm trying to think of an example where you literally just say good or bad, but I think most things are 1 to 5. YouTube, you say good or bad. So now let's break this, instead of up and down, let's break it into actual numbers. She said PlayStation's got a 3-star. He says PlayStation's a hard 5. We've got all the data that we had originally. We're just looking at it in a different perspective. So we still have these gaps. How do we figure those out? You may see that this looks familiar to how you might have been in like high school algebra. It looks kind of like a matrix. And specifically, it's a dense matrix. We know most of the data, but we still have some zeros and some gaps. How do we fill in those gaps? So we convert it to a matrix and it looks like this. Now we're starting to look at it more as a math problem as opposed to a generalized visualization. So using this matrix, what kind of linear algebra can we apply to discover an approximation for these users? And using low-rank matrix factorization. So basically it's just like you're in high school, you had a quadratic equation, you had to factor it into parts. But with this matrix, we're going to break down these large, dense matrices into products of smaller matrices. So this seems really complicated, but it's really not that big of a deal. All of this work has already been done by the developers who developed MLlib. And so you don't necessarily have to understand all of this, but it's good to have a general understanding of what kind of tools you're using. Low-rank matrix factorization is actually a minimization problem. We have some set of data, and we have a cost function that is going to describe our model that we've built. So how do we find the global minima of this problem? The issue with this kind of problem is that it's called a non-convex problem. What this means is it's really hard to find the global minima of this entire data set. You can through kind of a brute force search throughout the system, but the time required to find the global minima of a non-convex problem is exponentially related to the number of variables that you have available. So this is where the algorithm that we're going to use with MLlib comes in to help us. It's called alternating least squares, which is going to allow us to convert this non-convex problem into a convex problem. Once we have the formula in a convex form, to find the global minima of this problem, we just slide down the slope until we get to the bottom. And the issue with that here is, if you're right here, and it depends on what part of the graph you're on, if you're right here, you're going to look for the minimum, you're going to get there, but it's really a local minima, not a global minima. So by using alternating squares where it splits out the variables that we're trying to solve for, where we're only dealing with one at a time, it allows us to treat it as a quadratic convex formula. So getting back to the matrix factorization, it's a little introduction to how it actually works, but you don't really need to deal with all that. You need a basic understanding of what you're doing. As a developer, it's important to minimize how many black boxes you are using. But once you have a general understanding of how it's working, we can just use the actual work that MLlib is already built into the system. So let's take a look at some code. I have no idea how I'm doing on time, but I feel like I'm flying, so it's probably going to have to slow down a little bit. When we're building this problem I'm going to use Python. We're going to use MLlib on Spark. The first step we're going to do is collect our data. So in this situation, we're going to do a kind of a Netflix type scenario. We have a large group of movies. We have a large group of ratings on those movies by another large group of users. So we've got a couple different points into this data. This data set by Movie Lens actually has 20 million ratings on 27,000 movies by 138,000 users. So we've got quite a bit of data that we can use to solve this problem. And it looks a lot like this. It's just a CSV of tons of data. So if you go home and start to play with this, you may realize that this data set's about 10 years old, so don't look for a lot of new movies when you're building it. But this gives you a way to test your algorithms. Really, the only people who are going to have this real up-to-date stuff is Amazon and Netflix, unless you're in the business of collecting movie ratings from users. You then have your ratings yourself from your users in your system. And it kind of breaks out to a user ID, a movie ID, and a rating. So this relates back to the movie ID. And then we then have a rating with a movie ID and a user. That's where we can then build that graph that we were looking at earlier, the connections between users and products, and on a 1 to 5 scale. So at this point, we'll pull in MLlib. And this is just about how easy it is to have access to the algorithm that we're using. So you could see while I was trying my best to explain the really complicated math that math majors and academics figured out who knows how many years ago, now that it's been done, we have the benefit of just using it like this. We're going to pull the ALS algorithm from the recommendation package in the MLlib library. It's pretty simple at this point. So we have a large set of data. We have the movie reviews, we have the ratings, we have the users. We need to split that into chunks. We need a testing chunk. We need a chunk of that data for our training our models. And we need the other larger set of it to build our larger model that will apply to the actual production data set. So while we're doing that, we get to use a really cool function from Spark called random split. And so what this does, before this similar function, you'd probably say I have 1,000,000 rows. I need a 10,000 row training set and a 15,000 row test set, but a lot of this data, a lot of these algorithms are really dependent on the fact that you have truly randomly sampled data from your set. You can't necessarily just grab the first 10,000 rows and say, this is my training set, and the next 15,000 rows, this is my training or my test set. You need a true random sample. And so you can imagine how you'd go to build this sort of iterative thing. You'd start generating random numbers and looping through and grabbing IDs from the array. Random split has a really nice function where we just give it ratios and say 70% of this complete ratings data I need to split off to my training RDD, 30% of it I need to split off to my testing RDD. So this is not grabbing the first 70% and assigning it to the first Python variable. It's doing a random sampling of 70% representative of that data set, which I found pretty cool because I would have probably done 50, 60 plus lines doing some random sampling function myself. So now that we have the data split into sections, we need to actually train the model and tune the parameters. So in every model, there's certain parameters that must be tuned. It's kind of a misinterpretation of machine learning from the outside that machine learning is this smart robot that just knows how to do what we tell it to do. It's basically just a model, which is a graph, that's going to fit some graph that we wish it fit. So a lot of people have found models that are approximately very close to describing some situation in nature, but we still have parameters in that we have to tune. Think of it as little knobs on like a music deck, like for if you're a DJ, and you need to tune that one to 2, and you need to tune this one to 4. And so we have these parameters that we need to tune to make sure that our model is closely fitting to the reality of the data that we expect. So we have these different parameters that are sent into the ALS algorithm. The one we're going to focus on here is ranks, which is how many ranks we split our matrices into in order to factor it out into smaller matrices. We don't know what's best, and so that's the key kind of takeaway to think about is we don't know what the secret is to these algorithms. We just know that we can approximately discover it through, we often use other statistics methods like gradient descent to find what's the best function. So here we're going to iterate through these ranks. And so I apologize for how small this text is. Putting code on a slide is not the easiest thing. But we're going to iterate through these ranks and discover, we're going to train models. So we actually are going to train multiple models based on those multiple parameters. And we have a good measure for gauging the error of the models that we've trained. It's called the root mean square error function. It's just a little function that we run on the data that outputs a number. The lower the number, the less error there is in the actual model. So we've gone through and iterated through our movie data and predicted against a test set what our RMSE might be. You can see here that the best model is actually trained with rank A. So this is before we actually even train our production data set. We need to train a few models to do testing on if that model is correctly going to demonstrate our data. So using the rank 8, we're going to continue to build the model with our own ratings. So now we have our new ratings. These are ratings that, in this situation, if you do it yourself, it'll probably be your ratings that you feel about these movies. But imagine it's ratings from users in your system or ratings that you're gathering from a new data set that is not represented in your own data set. So we build this new ratings data set. It's split into first index is a user. The second index is the movie ID, which relates back to that movie database that we had previously. And the last one is our rating. So these are actual movie IDs from the data set. I rated Star Wars as a 4 and Time Cop as a 1. They're both awesome movies, but kind of different. I don't know if you've seen Time Cop, but Jean-Claude Van Damme is naked in the first 30 seconds, and it really freaked me out as a child. But after we build that data set, we need to build a new RDD. And when we build the RDD, we're going to parallelize it across our cluster And this function here is what actually deploys that RDD to our Spark cluster. And once you've deployed it to your cluster, you can actually see new jobs developing in the Spark console. If you've ever used Hadoop, you may have seen a similar console with the Hadoop console. You see the MapReduce jobs running, what percentage of the way they're through. With Spark, it's similar, but as you can see, much cleaner and nicer application. It actually triggers these jobs when I was actually doing it from the Python console, which I thought was really interesting. It's much more interactive than Hadoop. You're doing a lot of deploying jobs to a Hadoop cluster, and it just feels very disconnected. You can actually log into a Python console with a Spark context and do these calculations manually right there in the Python console. So we've now distributed our rating data set to the cluster. We've previously distributed our whole training set to the cluster. So now we need to train a new model based on our ratings. So we use the union operator in Spark, which will take two RDDs and merge them together. And again, remember, this is not on one machine. This is across any n number of machines. It could be a 2-node cluster that you're running on Vagrant for testing, or it could be 8,000 nodes in Palo Alto at Yahoo or some crazy crap. So we're going to iterate through those, union them together, and then do a new prediction given this union data set with the model that we created earlier and we trained with our testing data set. And so just by doing this one line, this predict all, it comes back with a set of data. And now we can now see that given the ratings that all of my friends had done in the data set, given the ratings that I input after that, Silence of the Lambs is pretty high up there, Saving Private Ryan. So it's pretty obvious in a lot of ways. A lot of the best movies are going to bubble to the top, but you actually have mathematical proof to show that these movies are generally liked among a large group of users. So the important thing to note here is you don't have to be a data scientist to start getting value from these tools. You need to do a little bit of research to figure out what tools you need, how they're actually working at just the lowest level you can possibly get to. And you can use these without having a PhD in math. In this set of algorithms that are available in, that's way too far back to go. I was going to show you the list of the algorithms that are available. Using this one library, you could run large portion of the analytics on your business by only using one discrete library. You don't have to span out into another system. You don't have to hire new people. It's just one kind of central area. And there's a lot of libraries that focus on one specific thing and they get really good at it. But MLlib is trying to localize all of that knowledge into one component that's core to Spark that we can then use in our business. I'm not really good at this button thing, but that is essentially